This is my presentation on the analysis of goal-oriented requirements engineering methodologies for legal requirements. The goal of this project is to provide a literature review of GORE methodologies for legal requirements, introduce several GORE methodologies, use these methodologies to model example requirements for HIPAA, and finally to compare and contrast the effectiveness of these methodologies. The methodologies discussed in this paper are Legal GRL, I-STAR Framework, Chaos, GBRAM, Nomos, Agora, and Tropos. For the scope of this paper, the segment Reasonable Safeguards has been chosen to demonstrate the GORE methodologies. The Reasonable Safeguards segment states that a covered entity must have in place appropriate administrative, technical, and physical safeguards that protect against uses and disclosures not permitted by the privacy rule, as well as that limit incidental uses or disclosures. This language leaves a lot of room for interpretation. It gives instruction on what to do, but not how to do it. The following example requirements have been written to support this goal of providing reasonable safeguards. The system shall log out a user after 15 minutes of inactivity. External entities performing research must declare intent before being granted access to the data. The system shall anonymize any data given to external entities for research. We'll start with Legal GRL. Legal GRL is an extension of GRL. It uses the same symbols for actors, goals, and tasks, as well as the same contribution, dependency, and decomposition links. The main difference between GRL and legal GRL is the ability to edit the metadata of an element. The metadata can be altered to make a GRL element correspond to a legal construct, such as a permission or obligation. This allows software components and legal constructs to be modeled in the same diagram. An important feature inherited from GRL is the compliance analysis. By setting the satisfaction level of a task or subgoal, it becomes immediately apparent if a goal has been satisfied. The next slide shows a concrete example with the requirements that support the HIPAA regulation. Here we see the data controller's goal of providing reasonable safeguards for personal data. The data controller has the task of disclosing data to external researchers if the researcher's intent is deemed acceptable and the data is anonymized. Notice that disclosing the data negatively impacts the goal of providing reasonable safeguards. Even with the precautions of anonymization and proper intent by the research team, a disclosure still poses some risk. The system user's task of logging out after 15 minutes of inactivity supports the high-level goal of HIPAA compliance. In this example, the intent of the research team is decided to be unacceptable. Thus, a disclosure does not take place and the high-level goal of providing reasonable safeguards is strongly satisfied. If the intent had been judged acceptable and the data was disclosed, the goal would be weakly satisfied as a majority of contributions are positive. Moving on to the I-STAR framework. I-STAR is a graphical representation of goals and requirements like legal GRL. In fact, legal GRL is an extension of the I-STAR framework. This section introduces the strategic dependency graph form of I-STAR. In the SD graph, goals and subgoals depend on actors, which depend on tasks performed by other actors. With the I-STAR framework, it is easy to see how the actors depend on each other to fulfill the goal. The data controller depends on the declaration of intent, which depends on the external research team. In turn, the external researchers depend on the data controller to anonymize any disclosed data. System users depend on the task of being logged out after a period of inactivity. And finally, the goal of providing reasonable safeguards depends on all the actors performing their functions. Now we're going to do chaos. The aim of chaos is to build models and derive requirements documents. In a chaos model, each goal is justified by at least one other goal. The purpose of this is to show why goals have been introduced into the system. Goals in a chaos model are further refined and divided into subgoals in order to describe how higher level goals are to be met. In the HIPAA example, the goal of providing reasonable safeguards is divided into functional and non-functional subgoals. The subgoals can be further broken down into operations performed by agents. In this example, the goal to disclose data as safely as possible is broken down into two operations: anonymization of outgoing data and declaration of intent for data. This diagram also shows which agents are responsible for which subgoals. The graph also identifies what operations support which goal or requirement. It is easy to see that more goals and subgoals could be added to this diagram. One of Chaos's strengths is that goals can be continuously broken down and refined, thus providing developers with smaller and more clearly defined goals and requirements. Now we're going to do GBRAM. Unlike some of the methodologies already reviewed, GBRAM is not a graphical representation of goals and requirements. GBRAM is an iterative process that aims to uncover high-level goals through identification, organization, refinement, and finally elaboration. A notable strength of GBRAM is that all goals do not have to be present from the very beginning. GBRAM is intended to identify new goals and requirements. The following tables represent the iterations of GBRAM. Table 2 shows the initial state, where only the highest level goal and stakeholders are known. After refining the goal to provide reasonable safeguards, 3 subgoals are identified, shown in Table 3. Note that this process identified additional agents and stakeholders that were not present in the initial state. As part of the refinement and elaboration stages of the process, the obstacles and scenarios columns have been added. These columns are optional and added as needed in order to clarify the requirements or processes. They're split up here to illustrate the iterative process, but the final product would be a combined table of tables 3 and 4. Nomos is a modeling framework used specifically for legal compliance. Nomos allows requirements engineers to build a model with exceptions, derogations, conditions, and cross-references. Nomos is good for determining what set of legal norms hold under given conditions, as well as finding alternate methods of compliance. As Nomos modeling depends on precise legal requirements, knowledge of legal phrasing is required. The newest version, Nomos 3, allows values to propagate through relationships to measure the level of compliance to legal norms. The HIPAA Nomos diagram represents 3 norms: D1, D2, and D3. All 3 norms are of type duty. Each norm has a holder or party responsible for satisfying the norm. In this diagram, holders are identified by the role symbol. The data controller is responsible for fulfilling D2 and D3, while the external research team fulfills D1. D2 has conditions on its satisfaction called the antecedent. When utilizing Nomos 3's compliance analysis tools, it will become apparent which norms hold and which do not. In the event that a norm does not hold under a specific instance, new norms could be added to ensure the satisfaction of a goal. The Attributed Goal-Oriented Requirements Analysis, or AGORA method, is a graphical representation of goal-oriented requirements engineering, similar to the ISTAR framework, but adds additional attributes such as contribution values and preference matrices.